Hello, good morning everyone. My name is Shochan and today we are going to talking about irreducible matrices which I'm going to give a presentation on today. I'm from the CFC department and let's get started. Introduction to the topic and what we are going to do today on this is overview on M matrices and the significance, importance of irreducibility in matrix theory and application in various fields such as in mathematics, in control theory and in economics. These matrices are important in this control theory and mathematics, and there are various fields in which they can be applied, such as control theory and economics. Coming to the topic, what is in a matrix? A square matrix with non-positive off-diagonal entries and a positive diagonal. A square matrix in which all the off not elements which are not in the diagonal elements are non-positive, which means they are all negative or either zeros or and the diagonal is only positive. Only the diagonal elements are positive. Coming to the formal definition, the matrix A is an M matrix if A is equal to Si minus B, where B is a non-negative matrix and S is a scalar. A non-singular M matrix that is reducible has a strictly positive inverse. All entries are greater than 0. In the formal definition, they say that S into I minus B, where I is equals to an identity. An identity, the diagonals are positive, and the other elements are all non-positive or negative, which are zeros. So this explains the matrix definition. In the non-singular matrix that is reducible has a strictly positive inverse. All entries are greater than 0. Coming to the properties of M matrices, all principal minors of an M matrix are positive. When you do the minor of an M matrix, they're always going to be positive. All principal minors, when you do the M matrix, are positive. The inverse of a M matrix, if it exists, is also a matrix. Uh, in some cases, the inverse may not exist, but if it exists, it's definitely also going to be a M matrix too. And that matrix too is also going to have principal minors of being positive and its inverse to having, if it exists, also being in a matrix. The cycle continues. The diagonal elements are non-negative and at least as large as the sum of the absolute values of off-diagonal elements in a row. The diagonal elements which are not non-negative, which means positive, and which are at least as large as sum of absolute values of off-diagonal elements. Even if the sum of all off-diagonal elements are combined, uh, may not be equal to diagonal elements in of each row. Coming to what is an irreducible matrix. Definition of reducible matrix. A matrix is reducible if there exists a permutation matrix P such that P inverse of AP is block triangular. This says that the permutation matrix P, which inverse is multiplied by AP, is going to give a triangular matrix. Irreducibility condition. Matrix is irreducible if it cannot be transformed into block triangular form by a permutation. So if a matrix is unable to be transformed into a block triangle form by a permutation, it's going to be an irreducible matrix. And so starts the main topic of irreducible M matrix. Irreducible M matrix is a matrix in which if it is both an M matrix and is a irreducible matrix. In other words, there is no permutation matrix that transforms a matrix into a block triangle form. So it's a matrix which combines both the M matrix and an irreducible matrix. So in this irreducible M matrix, permutation matrix, there is no permutation matrix that transforms M matrix into a block triangular form. Here is an example of a M matrix, as you can see here. It has non-positive diagonal entries. As you can see, only the diagonal elements are positive, the 4, 4, 4. All the other elements are non-negative, such as -1 and 0. This is also not positive, so it's also a non-negative one. -1, -1, 0, 1. Uh, so by this basis, we can say that it cannot be transformed into a block triangular form by a permutation, meaning it's irreducible. So by determining the diagonal row and the non-diagonal elements, we can determine it's a irreducible or not. Coming to irreducible M matrices, combining the concepts of M matrices and irreducibility as we talked earlier, we can determine that an irreducible M matrix is a matrix that cannot be split into smaller block M matrices through row and column permutations. Due to it being not being reducible, uh, this matrix cannot be split into smaller blocks, and so uh, through row and column permutations, it's not able to do any permuting abilities. Coming to key properties of irreducible M matrices, it has spectral properties. Example, non-negative eigenvalues. If you try to do an eigenvalue of this particular M matrix, you're gonna get the eigenvalues you're gonna get is also gonna be non-negative. Something like a negative and a positive eigenvalue or zeros. Uh, Existence and uniqueness of solutions to systems of linear equations. Uh, from this irreducible matrices, you can prove the existence and uniqueness of solutions to systems of linear equations. In systems of linear equations, the existence and uniqueness of solutions may get frequently by using these matrices. It also has, there are also stability properties in dynamical systems. Uh, Applications of irreducible M matrices. Uh, these are used in study of Markov chains and stochastic matrices. Uh, this irreducible M matrices are important in Markov chains and stochastic matrices. These are other types of matrices, and Markov chains are chains which are used by the matrices. And it also has applications in network theory, control systems, and optimization problems. And these are using control systems to determine and do the control flows. Coming to the Perrin-Frobenius theorem, the Perrin-Frobenius theorem is for irreducible non-negative matrices. Importance of this theorem is in characterizing the spectral properties of irreducible matrices. The spectral properties we talked about earlier. This theorem focuses on characterizing the spectral properties of this irreducible matrices. Here's an example of irreducible matrix. How are we going to be able to determine this is an irreducible matrix or not? We're gonna do that. The determinant of this matrix is non-zero, meaning it's invertible. If you try to do the determinant of this matrix, it's gonna be a non-zero. So it's invertible. Uh, Non-positive entries. A12 equals to A13 equals to A21 equals to A23 equals to A31 equals to A32, which is all gonna be equal to minus 1 of A12 is equals to A21 equals to A23 equals to A31 equals to A32, which is also equals to minus 1, which are all non-positive, which means negative. Non-diagonal entries are positive. Non-diagonal entries are negative and diagonal entries are positive, which as you can see here, A11, A12, A1, A3, A33, which are all equal to 4, which is greater than 0, and A11 and A22 and A33, which are all equal to 4, which is also greater than 0. Irreducibility. The matrix is irreducible because for any power of the matrix, uh, all entries become positive, showing that it's possible to reach any row from another row. So if you try to do uh, any power of matrix A2 or something, and you can reach a row from any other row. Ferrand-Frobenius eigenvalue, the largest eigenvalue of an irreducible M matrix. This eigenvalue is significant in many applications such as stability analysis. This Ferrand-Frobenius eigenvalue is discovered from the theorem, Ferrand-Frobenius theorem we discussed earlier. The theorem focuses on spectral properties, and by using this eigenvalue, you can use it in many applications of stability analysis and control flows and control structures. Stability of systems involving irreducible matrices. Used in stability analysis of dynamic systems, example differential equations and control systems. It has relation to system behavior and equilibrium points. These matrices are used in differential equations and control systems, as the control system we talked about earlier, to control the flow of various programs and various applications. And you can also determine the stability and do the analysis of them by using dynamic systems, and also has relation to system behavior and equilibrium points. Um, Coming to further results on irreducible matrices, it has an existence of positive solutions for linear systems. It shows when you try to do linear systems by using these matrices, you're mostly going to get the positive solutions, and it also has relation to generalized inverses of matrices. So while doing this irreducible matrices, we're gonna be it has a relation to generalized inverses of matrices. Numerical methods for irreducible matrices. Methods for solving linear systems involving irreducible matrices. There are also many methods which are used to solve the matrices, as we discussed earlier, by using the Frobenius theorem, and can also do many other methods. We can discuss different numerical techniques for matrix inversion and solving these equations. And coming to challenges and research areas, current challenge in the theory and applications of irreducible matrices are many, because you can use it in many different applications, but it also has many numerical problems which may be taking a large amount of time to solve, and many things, open problems and areas for further research. There are also much scope for further research which you can do in the future, and it's also in the development process, so it may take a time. Coming to the conclusion, we can just get a recap or quick recap on what happened earlier. We discussed about the overview on the matrices and the significance. What is a matrix? What is properties of a matrices, and what is a irreducible matrix, and what is a irreducible matrix? Uh, a matrix is a matrix in which non-positive of diagonal entries and positive diagonal, which means a, a matrix A is equals to S into identity matrix, which is equals to minus B. It's a non-negative matrix and is a scalar. Irreducible matrix is a matrix which is, if there exists a permutation P inverse of AP is block triangular. So irreducible matrix is a matrix which is also irreducible, which means all its diagonal entities are positive and non-diagonal entities are negative. So it can be converted into a block diagonal form. Block diagonal form. It's uh, the irreducible matrix inverses are also a matrices only, if there exists one. Um, Significance of irreducible matrices and mathematical engineering concepts. These are irreducible matrices are very much important in control systems and are used in many sorts of engineering contexts. And coming to the references, the websites are used to take references for Science Direct and Stack Exchange, and some of the references are taken from different sources and websites on the internet. And thank you for listening to the presentation, and I hope I'm gonna do well.